Hi guys, how are you getting on? Hope you're all keeping well. Now time for our next lesson. So we're going to be looking at power, voltage and current and how these all link together. We've actually kind of looked at each of these kind of individually in the past. We've looked at voltage and current together a little bit. Now we're going to try and just link the three of these kind of quantities together and see if we can't come up with a way to kind of move easily between the three of these, which is quite important when we are looking into electricity and electrical uses and uses of electricity. So our learning intention for today will be to further develop our understanding of power. Now I say today, it's going to be over probably 2 lessons. I'll do half of what we want to do here and we'll do half in the next lesson. So by the end you will be able to define power. Some of you should be able to do that already. In fact, most of you should be able to do that already. We have already looked into how to define power and what power is and the equation for power already. So if you're not sure of that, we will do a little bit of revision and you'll hopefully get you up to speed on that. Otherwise, it'll just be kind of a reminding you as to what power is and whatnot. You'll be able to state the equation that links voltage and current to power. That's really the kind of new bit, and that will be the derivation. That's probably where we'll stop today after we've done that. We're going to try and derive that equation from the initial equation for power. It is important just to point out that you don't need to remember the derivation if you're not comfortable with that. As long as you remember how to use each of the equations, that will be absolutely fine. You'll be able to use Ohm's law then to derive 2 additional power equations, and again, if you're struggling with the derivations, as long as you know how to use each of the 3 equations, that's what's important. I just personally always found it useful when I was at your stage to know how to get from one step to the next. And finally, you will be able to use these equations to answer questions, because obviously it's not good just knowing the equations, we need to know how to use them. Right, let's start with a little bit of revision. What is electrical power? Let's have a little think about that. What is electrical power? Well, hopefully we've all managed to get there. Electrical power is the energy utilised by a component, so for example a lamp or a resistor, every second. It's the amount of energy that lamp perhaps is using to light up every single second. We have our equation which links these quantities together. So we have P for power measured in it's measured in watts. E for energy measured in is measured in joules, and of course T for time measured in that is seconds, as always in physics. Okay, so that's our equation for calculating power using energy and time. Let's just throw all that to the side just for a little minute and let's have a look at current. What was current? Now this is something we looked at quite recently. We revised our understanding of current. We just tidied up that definition a little bit. So I'll give you a little second just to think about what current was. Hopefully you all remember this one. Electrical current is the amount of charge flowing in a circuit every second. It's the amount of charge that's flowing through that circuit every single second. Now we came up with an equation for calculating the current. The equation for calculating current using charge and time is here. So we have I obviously being current measured in amperes. We have Q being the symbol for charge measured in is measured in coulombs, and of course T still being the symbol for time, and time is still measured in seconds. Okay, let's throw this one to the side. Last little bit of revision. What is voltage and what is potential difference? So let's start off with voltage. What is voltage? So hopefully you remember this one. Voltage is the energy given to each coulomb of charge in a circuit. So it's the amount of energy that each coulomb of charge has in that circuit. So if you come across a coulomb of charge, it's how much energy that it has. So what was potential difference then? Just the very, very subtle difference then. What is potential difference? Now, hopefully you remember again, potential difference is the difference in the voltage between 2 points in a circuit. So if you're looking at connecting a voltmeter on either side of a lamp, that tells you the difference in the voltage on either side. So it's how much of that voltage is being, or how much of that energy is being used up to get through the lamp. So we combine them together. The potential difference then becomes the difference in the energy each coulomb of charge has when we look at them. When we look at that charge between 2 points in a circuit. So we look at how that charge has moved from one point to another. Now we haven't introduced an equation for which links these three quantities together at this point. The reason for this is the equation that we would need doesn't actually come in until higher. However, what I would like to do is just kind of write this as such. So voltage is equal to energy divided by coulomb of charge. So basically all we're saying here is that voltage is the energy per coulomb of charge, or the amount of energy that every coulomb of charge has. This is just another way of writing exactly what we've said there. We're just kind of writing it mathematically. So at this stage, what I'd like to do, let's just remind ourselves, V, voltage measured in volts, or potential difference also measured in volts. Energy is still measured in joules, and your charge, well, the answer's in there, it's measured in coulombs. And just to be completely clear, you do not need to remember this equation here. This has just been kind of introduced just to kind of show you how we get from one equation to the other at this point in time. So let's bring back those other equations that we looked at already. So if we bring these back, and then let's have a look and see what's happening here. We have our three equations that we've just introduced. So what we've got here is we have our first equation, P is equal to E divided by T. So power is equal to energy divided by time. We have the one we just introduced in the third set of revision slides there. Voltage equal to energy divided by charge. I've just kind of condensed charge down to just charge here. And of course we've got I equals Q over T. Current equals charge divided by time. So let's have a look at our equations. We want to find one, or we want to try and come up with an equation which will allow us to use voltage and current to calculate power. Now we've got an equation here for power. So let's start with the top line of this equation. We have energy here. So let's have a look at our energy equation. Our energy here, and we'll have a look at our other equations, and we'll see just exactly where we can find energy. So where's energy? Well, here's energy here. So let's just circle that one here. So let's rearrange this equation so that we can calculate energy. So if we rearrange this equation, all I'm going to do is I'm just going to bring charge over to this side here. I have to change this divide sign to a multiply sign when I bring it from one side to the other. Just the opposite sign, remember. And then just kind of switch them over so that we've got energy here equals voltage times charge. Now if energy is equal to voltage times charge, and we've got energy up at the top here, then we can say that this bit up at the top here, this top line is just equal to voltage times charge. So let's do that. Let's substitute that in, and we end up with power equals voltage times charge divided by time. So we're one step closer. We were looking to have voltage and current. We've now got a voltage here, but we've got charge and we've got time. Now some of the more eagle-eyed amongst you might see a nice easy way of converting from here to our final step. I'm going to just take us on the journey. We'll go do it step by step, just in case there's anyone that would like to kind of see exactly how we get from one to the other. So we've got this quantity now here on the top line, charge. So we've got charge here. Obviously, as we said before, the symbol for charge was Q. So Q and charge are the same thing. So let's just rearrange this. So we've got Q, or charge, is equal to current times time. Charge is equal to current times time. So again, we've got now charge here is equal to current times time. We've got charge up here. So what we can basically say is that this quantity here, this charge here, is just equal to current times time. So let's bring them over and substitute them in, and we end up with power equal to voltage times current times time divided by time. Okay, that gives us this equation right here. I'm just going to tidy that up just a little bit. So we're going to bring this down here. So we've got power is equal to current times time times voltage divided by time. Okay, I've just rearranged this slightly. Just we'll explain later on why I've kind of rearranged this into this kind of order. Those of you that are quite adept at maths will have noticed you've got time on the top and time on the bottom. Your time are both going to cancel out here. So if you get time on the top and time on the bottom, then they both cancel out. It's like having two numbers divided by each other. So if you have 2 divided by 2, you get 1. It's as simple as that. If you get 4 divided by 4, you end up with 1. 10 divided by 10 is 1. And if I do 1 times any number, so 1 times 100 just equals 100. 1 times 43 is 43. It is as simple as that. So let's just simplify that down. We'll cancel these out, and that brings us to our equation here. Power is equal to current times voltage, and this is the step that we were looking to get to. Okay, so we've now got an equation which links power to current and voltage. So let's have a look at this equation. We've got power here, our equation here, power, and power is equal to the current measured in amperes multiplied by the potential difference in volts. Okay, so if you know the potential difference across a component, so if you've got a lamp, let's stick with the example of a lamp. If you know the current going through that lamp and you know the potential difference across the lamp, then you're able to calculate the amount of power that lamp is using, so the amount of energy that lamp is using every second. That's a really, really important equation to know when it comes to electricity, because quite often in electricity we're looking to be working in this unit here, power, and we're looking to link it to energy and the amount of energy use. And as a society these days, we're kind of looking to try and reduce our energy use and whatnot. So we're actually able to use this equation to then calculate how much a component is likely to use and see which component is likely to be more efficient, for instance. So that's our equation here. Just in case you need it, here is the triangle. Just in case you like the triangle for rearranging the equations, feel free to take a quick note of this one if you need it. So the triangle, we've got power on the top, we have current and voltage on the bottom. So power goes on the top, we have current, and we have voltage on the bottom. As simple as that. Okay. Right. Let's have a look at a worked example then. So we have a lamp. Stick with the lamp. We're quite used to it now, and it has a current flowing through it of 0.15 amps and a potential difference of 2.1 volts. What is the power developed in the lamp? Okay, so what do we want to do first of all? Well, I'd suggest that we highlight our important information that we've got in the question here. So what bits of information are important here? We've got this here, 0.15 amps is our current, so let's write that down into our shopping list. 0.15 amps. We have 2.1 volts, our potential difference, 2.1 volts, and one other piece of important information, well, it's what we're trying to calculate as our power. So P is just equal to a question mark, so that's what we're trying to calculate. So the next step is to write down our equation. If you've managed to write down your equation, remember you get yourself 1 mark. 1 mark out of 3, that is, remember. So next we need to substitute in our numbers. So power is equal to 0.15 times 2.1. Again, get yourself a mark if you've managed to do that. Nice and simple. 2 out of 3. So let's answer that. We get power is equal to 0.315. Now let's just have a little look at this in terms of significant figures. We've got 2 here and 2 there, so we want to give our answer to 2 significant figures. So power is going to be 0.32 watts. Simple as that. Now, just to be clear on this, so that's your final mark, and obviously worth 3 marks in total. Just to be clear on this, you would get, as long as you included your units, you would get a mark for this here, because remember you're allowed 2 extra significant figures or 1 less. So we would have allowed the power equal to 0.3 watts, 0.32 watts, which is the ideal answer, and we would have accepted 0.315 watts as well. But this is the answer that we really would expect most of you to hopefully be coming up with by this point in time. So that is power, current and voltage. Now at this point I kind of want to stop. I don't want to overwhelm you. I was just going to kind of, initially I thought I would just kind of power ahead and we would look at Ohm's law and we kind of look at how we can incorporate that and derive the next equations. That's quite a lot to take in, so do take your time. Feel free to stop at this point, go back and watch it again. Just make sure that you have completely understood it. If you really feel like you're not understanding it, just make sure you know that equation that we came up with at the end, the power equal to the current times the voltage. So that's this one here in our slides. And then have a look at these questions. So let's have put this into practice. In the electricity and energy booklet, the question booklet, I want you to try all the questions on page 25 to 27. Okay, so give all of them a go. I've not quite decided which ones yet, but I might ask you to submit certain questions, and I'll ask you to do that. All I'll ask you to do is just to take a quick snap, a quick picture of what you've done, and just kind of upload it. I'll not ask you to submit everything that way. Just I'm looking for a quick picture, maybe 1 or 2 questions, just to kind of see how you've got on. Do remember to mark your own work as you're going through it. The answers are in the answer booklet, which is on the Google Classroom as well. And if you are struggling, if you can't figure out why you're not getting the right answers, ask questions. That's why I'm here, and I am here, and I will still answer questions. I may create a video kind of similar to this, or similar to what I did yesterday, to kind of help with the as I said yesterday, the other day, to help with the electric fields, and just to kind of clarify those electric field diagrams that were asked in one of the questions that I'd set. It may just be a quick simple text reply. Maybe I'll sketch something out and take a quick picture so you can see how to get to a final answer. It'll depend on what question you're asking, but I will do my best to kind of answer it as best I can for you. Once you've had a go at these questions, let's come back to your success criteria. Are you happy? Are you still need a little bit more work? Are you completely not understanding any of this? And remember, it's not the derivations you need to remember, it's just how to work with the equations that you need to be able to remember. So let's have a look and see which ones we've covered so far and which ones we can tick off. Now you obviously need to tick these off for yourself. If you're happy with them, tick them off. If you're not, go back through, look at the slides again. As I said, try and see if you can figure out just exactly how to get the right answer. And if you're struggling to get there, do ask questions. I'm more than happy to give you any help I possibly can to help you to understand this. And then maybe try some more questions, and then we'll kind of take it from there. So let's have a look and see which ones can we tick off. So I can define power. Well, as I said, hopefully we should have been able to do that already. If we couldn't, hopefully we can now. So I can define power. Good. I can state the equation linking voltage and current to power. Well, we managed to derive that equation, and so let's have a little look. Yep, tick that one off. I can use Ohm's law to derive 2 additional equations. We're going to come back to that once we've not done that yet. I'm going to put a little cross there, just purely because we've not covered that just yet. And I can use these equations to answer questions. Well, we've started to do that. We've looked at, obviously, questions which cover power, voltage and current. Next time we'll have a look at some questions which will cover power, voltage, resistance, current. These kind of 3, and we will be able to kind of link between the 3 nice and easily, hopefully. Okay, so that's it for today. Do make sure you try these questions. I will be uploading the second video either later on this week or possibly the start of next week. We'll have a look and see how long it's going to take you to do this. I don't want to overwhelm you with too much work, but I do want you to still be working and still continue to be pushing ahead with our learning. So we'll get the next lesson up either towards the end of this week or at the start of next week. And in the meantime, just keep yourself safe, and I will hopefully see you soon.